was no accident that Turner painted light when he did, or that light became the inspiration of the Impressionists. The nature of light became an obsession with the physicists, too. See, none of them could visualize how the light of the sun reached the Earth.
Why? What is the nature of light?
To understand the nature of light, you have to know what matter is made of.
I thought it was made of atoms.
What's an atom? Well, Newton thought it was small, solid particles. But that's not what scientists saw when they observed atoms for the first time. What they saw was totally unexpected and shocking.
You mean when they discovered that atoms were made up of even smaller particles, a nucleus with electrons whirling around it?
Not only that, they were moving in relatively vast regions of empty space. That's what shocked the scientists up. Atoms consist mainly of empty space.
What does that mean, vast regions of empty space? Atoms are tiny.
Yes, they are. This is what's so hard to visualize. See, the size of atoms is so far removed from our ordinary sense of scale and proportion that it's extremely hard to get a feeling for the relative sizes and distances of their particles. Ask yourself, how many atoms are there in an orange? Now, to answer this, you'll have to blow up the orange to a size where you can actually see the atoms. You'll have to blow up the orange until it's reached the size of the Earth. The atoms inside of it will then be the size of cherries. Myriads of cherries tightly packed into an orange the size of the Earth.
Wow, what an image. I'm serious. I was trying to shrink the Earth orange back down to the size of an orange and imagine all those cherries whizzing around inside of it. It made me dizzy. This is a dangerous height to be dizzy at. But okay, you say that the atom is the size of a cherry and that in that cherry atom there's all this empty space. Well, what about the nucleus? There is a nucleus in there, right? I mean, how big is that? That's where we're going here, isn't it?
Invisible is the answer. If we blow up the atom to the size of a football, the nucleus would still be invisible. If we blow up the atom to the size of a sphere that would fit into this room here, the nucleus would still be invisible.
What if you blew it up to the size of this island, to the size of the rock we're standing on?
Okay. We would blow the atom, the cherry, up to the size of this island. Okay, then the nucleus would be the size of a small pebble. Something like that. And the electrons would be much smaller still. We would have to look for them all the way down there at the edge of the island. And the whole space in between would be empty.
Wow, that's fantastic. It's weird. It's even weirder than poetry.
So what you're saying is that if there were a sphere large enough to contain this whole island, what it would actually consist of is a pebble and a few grains of sand. That's all this huge sphere contains. In other words, nothing. It's empty. But if this rock is made up of spheres like that, then what makes it so solid? Why can't I pass my hand through it? Why don't we fall through it?
Yeah, why don't we fall through everything? Why doesn't everything fall through everything?
Well, you see, this is the obvious question that physicists had to ask. Now remember that all the Newtonian concepts were based on things that could actually be seen, or at least visualized. But what they were now finding in this strange and unexpected world were concepts that could no longer be visualized. And when they went on battling with this absurd phenomena of atomic physics, they were forced to admit to themselves that they didn't have a language, not even an adequate way of thinking to describe their new discoveries. They were forced to think in entirely new ways in terms of radically new concepts. To understand why matter is so solid, They had to question the conventional ideas about the very existence of matter. And after many frustrating years, they were forced to admit that matter does not exist with certainty in definite places, but rather shows tendencies to exist.
Tendency? What the hell does that mean?
Now, let's say we want to observe an electron out there. Now, we cannot say that it is in a definite place. We can rather say it has a tendency to be out there in the front rather than in the back. Or here to the left rather than over there to the right. In scientific language, we actually don't speak about tendencies. We speak about probabilities.
I seem to remember voting for a bill in the Senate that gave some physicists a lot of money for a detector that they said would tell them exactly where an electron is. Were we being gypped?
Not at all. The strange thing is that when you actually make a measurement of the electron, it is in a definite place. But between measurements, you cannot say that it is in a definite place or that it has traveled a definite path from one place to another.
You mean when you want to measure it, it just sort of shows up?
Yeah.
Oh, kind of like out-of-work actors or presidential candidates like Jack Edwards. What do you think? What do you think? Hey, tough guy.
Yeah.
Oh, my knees hurt.
Okay, let me get this straight. You measure it and the electron is there. It shows up, like Thomas said. But in between measurements, you can't say for sure that it's in a definite place, or even that it went on a definite path from one place to another. So how does it go from here to there? It moves, doesn't it?
No.
You mean it stays in the same place?
No.
Well, wait a minute. Either the electron moves or it doesn't move.
Well, you can't say that. Well, are you getting a feeling now of what these physicists felt? You see, an electron doesn't move from place to place, and it doesn't stay in one place either. It manifests itself as probability patterns spread out in space. And the shape of these probability patterns changes with time, something which might seem like movement to human perception.
Are you saying that the electron sort of gets smeared out over a large region, and then when you measure it with the measuring gun, it collapses into a small point?
You got it. You see, all subatomic particles, electrons, protons, neutrons, manifest this strange existence between potentiality and reality.
So at the subatomic level, there are no solid objects.
No, there are not.
Well, if there are no solid objects at the subatomic level, how are there solid objects at any level?
That's the amazing thing. This simple question, what makes this rock so solid, goes way beyond our power of imagination. I mean, I cannot explain this to you in visual terms. Of course, I can do it in mathematical equations, but there's no metaphor for it.
How can you live in a world that's unmetaphorical? I mean, you have to perceive reality in some way. I mean, this is solid.
Okay. Let's take an atom from within this granite, a silicon atom with its 14 electrons. Now, the probability patterns of these electrons arrange themselves like shells around the nucleus, each shell containing several electrons. Now, within the shells, the electrons are everywhere at the same time, so to speak. But the probability patterns that resemble shells are extremely stable and very hard to compress.
Matter is solid because probability patterns are difficult to compress.
That's as good as it gets.
So I was right to sleep through Mr. Giddis's physics class. That little model he made out of Tinker Toys with sticks and balls, that was wrong, right?
Right, wrong. Yeah, it's a lousy visualization, but then no one did it any better.
If the doors of perception were cleansed, everything would appear as it is, infinite. William Blake. So, Sonia, life's a bunch of probability patterns running around. Probability patterns of what?
Of interconnections.
What?
Well, what I'm trying to say is that these probabilities are not probabilities of things, but probabilities of interconnections.
See, Jack, that's what she was trying to tell you.
See, we tend to think of subatomic particles as some kind of small billiard balls or small grains of sand. But for physicists, a particle has no independent existence. A particle is essentially a set of relations that reach outward to connect with other things.
What are those other things, please?
They are interconnections of yet other things, which also turn out to be interconnections, and so on and so on. You see, in atomic physics, we never end up with any things at all. The essential nature of matter lies not in objects, but in interconnections.
Ah! Everybody knows the chord. It's a third, the most basic of harmonies. Carries with it a very distinctive feeling, no? And yet, its individual notes carry none of that feeling. Therefore, the essence of the chord lies in its...
Lies in relationships.
And the relationship between time and pitch...
Makes melody.
Makes melody. Relationships make music.
Relationships make matter.
Music of the spheres.
As Kepler said.
And Shakespeare before him.
And Pythagoras before him. Now, this vision of a universe arranged in harmonies of sounds and relations is no new discovery. Today, physicists are simply proving that what we call an object, an atom, a molecule, a particle, is only an approximation, a metaphor. At the subatomic level, it dissolves into a series of interconnections, like chords of music. It's beautiful.
Yeah, but there are boundaries, aren't there? I mean, between you and me, for instance. We are two separate bodies, aren't we? That's not an illusion. Is it? Are you saying that there is actually a physical connection between you and me and between you and the wall behind you and the air and this bench?
Yes. At the subatomic level, there is a continual exchange of matter and energy between my hand and this wood, between the wood and the air, and even between you and me. I mean, a real exchange of photons and electrons. Ultimately, whether we like it or not, we're all part of one inseparable web of relationships.